The reproducibility 8071R is the estimated reproducibility of the laboratory population in the program for that sample. So there are between 9 and 12 labs that are participating in these 5 samples for 8071. And on this slide, I'm comparing the reproducibility of the population of the OFID 5599 labs. So there's about 60 labs reporting ethanol by ASTM D5599. And the reproducibility of the results achieved for these 5 samples for 8071 are represented in the light blue bar. And we're comparing it to the dark purple bars, the reproducibility of 5599. When I look at all the published precision statements for ethanol, for multidimensional techniques in the OFID and even DHA, 8071 has the best precision. And so that's important to renewable fuel companies and ethanol producers. So the next 3 slides, this one is for the reproducibility of the olefins, and we're comparing the light blue bar for olefins to the 1319 in green and the SFC in red for those 5 samples. So once again, this is not the published reproducibility, it is the estimated reproducibility from the results submitted to the program. This is for aromatics, comparing the reproducibility of 8071 to the referee 5769 mass spec. And now for benzene, here we're comparing 3 different methods. So the 8071, once again in blue, the 3606, and the green mass spec method, and in orange 5580 for benzene. So I'll just summarize 8071 and saying that it has, it's very highly productive. So there's a 34-minute automated run. This saves a lot of labor, and you can consolidate the 8071 or combine it with the platform into multiple methods. It is got a lot less complexity. So there's no deuterated standards to add to calibration curves. There's no calibration curves to generate. You can set it up in a production mode that is automated, but you can also take it to another level and expand it to an R&D instrument. So just like a mass spec, it can be used for many different purposes other than set methods. The VUV can be used for many different purposes as well. We combine things and make things way efficient by replacing multiple techniques with a VUV. And I've shown in this presentation the precision that is superior, not just the published precision, but what's happening in the real world. It all results in significant cost savings, and we now have recognition by regulatory bodies of 8071. And I'll just finish it off with the picture of the VUV analyzer, and just let you know about we've seen the performance and the proficiency and the precision, and all of this is gained by the adoption of new technology and innovative technology in a VUV detector. So I think I've left room for questions, and I'll turn it over to Katie.
Awesome, thanks so much, Dan. We do have some questions coming in. Just a reminder, if you have one, that you can type it in the chat box on the lower right side of your screen. Dan, the first question is a 2-parter for you. Question 1, any plan to redo D5580RR to get better precision than current published precision in order to be used for CARB and EPA benzene and aromatics? Second part, any plan for correlation between D8267 to 1840 for naphthalene?
Okay. The first question there about the 5580 is the published precision for 8071 versus 5580 benzene. There's no problem there. The published precision of 8071 is actually a little bit better for the benzene, but the published precision for the total aromatics for 8071 versus 5580 is the 5580 is a little bit better. So I think for that, we are going to wait and collect more data from the ASTM RFG program. And that way I can take that to CARB and see if they will accept that. I know that CARB is fairly strict, and they just look at the and make a decision on that. So to be determined on the total aromatics yet, but and then the second question about 8267 for the diaromatics on the jet fuel. So one of the things why I mentioned the scope and the scope extensions is that when we did the ILS for 67, we based our diaromatics on a target of the maximum 3% in 1655, and we based that on some data of mass percent from HPLC and SFC data. And when we did the ILS, it fell just short of that 3% target, which is in 1655. So I think our scope goes up to, off the top of my head, about 2.5 or 2.6 mass percent naphthalenes or diaromatics. And now no jet fuel actually is as high as that. And what happened was we didn't validate into it because I was under the impression that you would have to have a method that covered the concentration in the specification. But just recently, the Jet Fuel Committee, ASTM Sub J, is accepting another technique that the scope doesn't go over 3%. So if we can demonstrate, they're accepting demonstratable data that the technique can measure at above 3%. So we can do that. It's another thing on my to-do list is to approach Subcommittee J and give them some data demonstrating that 8267 can measure over 3%, and then we'll be able to replace the 1840 naphthalene in that specification. One more thing is that we are also undergoing a project to do the formal 6708 of 8071 versus 5769 for benzene. So that project is underway too. So we'll be balloting that soon.
Great. Our next question is, what are the advantages of GCVUV over GCFID, as both methods detect all the compounds that you have mentioned?
The advantage of the VUV would be the three-dimensional data that I mentioned. So with an FID, a compound is identified solely on its retention time and quantified by the peak amplitude. With VUV, the compound would be identified not just by its retention time or its amplitude or absorbance, but it would also be identified by a spectral match to the library.
Great. The next question is, D8071 approved for use in India? And if so, list the fuels for which D8071 can be used. What is the estimated savings by using D8071 versus other methods?
In different jurisdictions of the world and different specifications, if you're looking at national specifications, you would have to champion and get 8071 qualified into national specifications. And so We're about halfway through that effort in Europe with developing methods that would be suitable for EN 228. We've been successful in the US and Canada, and in India or other parts of the world, those national specifications would need to adopt 8071. And in order to adopt a test method, the criteria usually is, has it been developed by a recognized standard writing organization? So 8071, yes. Does it have a valid precision statement? 8071, yes. And so there's no reason why it should not be adopted into any national specification. And it's certainly applicable to a wide range and of parameters. And so I would say in India, hopefully we can get some champions to adopt it in their specifications.
Great. Next question is, how compatible is the VUV analyzer with various models of GC? I work predominantly with Agilent GCs.
So our customers predominantly have Agilent GCs as well. But as you see in the picture here, the detector is similar in size to a mass spec, and it uses a transfer arm similar to a mass spec. So if you can actually connect this detector to any GC that can tell the VUV to start and stop collecting data and program sequences. So we've had it on multiple GC platforms.
Got it. I think you answered the first part to this question, but how are the different methods selected? And are there any valves or traps that need to be reconfigured each time?
How are different methods selected?
Yes, I think like on the instrument, I think you just mentioned that one in your last question.
Right, yeah, so it depends on the parameters and what you need to analyze, and so the skill of connecting the column to the detector versus trying to optimize valve timing. We said that the 8071 reduces complexity, and that's one way that 8071 can reduce complexity is you can eliminate the need for complex valve techniques.
Great. And then what kind of calibration does the analyzer require?
We require a retention time standard. So we run a mixture of N paraffins or a standard to define retention indice windows to look for identifying compounds. This standard also checks the GC. So our techniques right now are on a splitless injector, so we can look at split linearity. We can evaluate leaks, and the standards we also have either benzene or naphthalene in it, so we can fine tune the amount of sample that gets to the detector or the flow cell, and thus standardize that across many different detectors. And once we standardize how much is in the flow cell, we know that based on physics and Beer's law, that X number of molecules in that defined flow cell will give you an X amount of response. So in that way, we are able to break free from calibration standards, if you will, and or internal standard techniques. We've also got, I mentioned the check standard, so that's kind of a certified QC standard, if you will. So you run that and make sure that you hit the targets as well. So very easy to calibrate and set up. After that, totally automated.
Great. And our next question is, what is the expected applicable concentration range for FAME testing in the diesel biodiesel? And does it have trace levels?
It does not do trace levels, so it would not be suitable for, say, the 100 or the 50 or 100 part per million jet fuel specification. But what it would do in diesel is quantitate FAME regardless of feedstock. From 2 to 20% is our target. One of the things, it's not primarily a FAME in diesel method, but what it is a method that you can quantitate mono, di, and tri plus aromatics in diesel without worrying whether the sample has biodiesel in it or not. So you don't have to worry about it damaging columns or affecting your instrument in any way.
Great. Well, that was all of our questions for today. I'd like to thank our presenters for sharing their in-depth knowledge with us. Thank you for attending today's webinar, and have a great day.